Welcome back to Numerical Methods. Today we're going to wrap up our discussion of initial value problems by discussing adaptive methods and stiff systems. As a reminder, last time we wrapped up our initial discussion of initial value problems. We have talked about Euler's method, Schoen's method, the midpoint method, and fourth order systems, and how we can use this to solve ordinary differential equations. We even touched upon some of the topics that we'll do today, where we started saying we need some of these more advanced methods and or much smaller step sizes if we're going to solve complex problems. We're now going to talk about how we can maximize the efficiency of these systems by taking an adaptive or multi-step approach to solving these problems, and then hopefully we can be more efficient as we solve these equations. Specifically, we're going to talk about adaptive methods, including the Runge-Kutta-Fehlberg and the step halving method. And then we'll talk about multi-step methods, such as the non-self-starting Schoen's method. And then we'll talk about various stiffness approaches, particularly the implicit Euler's method. Then we'll go through, in each of these cases, we'll talk about some built-in MATLAB functions for solving these, and then we'll talk about different quote-unquote events that we can look at in MATLAB to help our code do what we want it to do. But first, let's talk about multi-scale systems, which are going to be sort of the general topic of today. A lot of times we see ODE problems where we start off with a nicely behaving ODE, and then we have this sort of spike. All of a sudden, we see very rapid change over a very short length scale. This is indicating that something is changing very, very fast. This is called a multi-scale system because we have one sort of scale happening here, so relatively gentle slope, and then all of a sudden we have this very large slope, and then maybe it goes back to being gentle again. So the step size that I would need to resolve that middle piece is very different than the step size that I would need to solve those end pieces, right? I would need to look much, much more carefully there, and not just along that scale, but where, particularly as I'm changing that size. So we need to have other methods that are going to adapt and try to figure out how big of a step it should take so that we can take relatively few steps at these long time scales, at these less steep systems, and we can spend our computational resources addressing these areas of high change. The first approach that we're going to take are called adaptive approaches to solving these. And the two primary approaches that we're going to look at in adaptive step size control is step halving, where we're going to perform one step of the algorithm in two ways. So one where we take the full step and one where we take two half steps, and then we can compare the results to tell us if we're accurate enough. The second method is going to be called an embedded Runge-Kutta method, where we're going to perform two different Runge-Kutta iterations for different orders and see how the results are going to go. This is the more preferred method, as it's going to give us higher accuracy. But first, let's talk about step halving and how this might look. So the idea behind the step halving is we're going to start with our point. Let's say we're sitting right here. We're going to take the tangent of that line just like we normally would and project out one iteration, so of length h. This might put us up here. I'm showing this in blue so we can differentiate it from the next step. So we've taken one full step just like we normally would. Then what we do is we take two half steps. The idea behind this is instead of moving all the way along that blue line to say t equals 3, we stop at this t equals 2.5. When I'm at this point, I'm going to calculate my tangent again. This should now give me a step that's going to point down this way. And then I take that next half step and I end up sitting here. We then look and see what my error is. So I can look and see, are these almost the same? Yes or no? I want you to note that this error shown here is generally not given as a percent. Right? So I take the difference between the two steps, and I'm usually not going to look at a percent, because in this case, I don't care if I'm like 5% off, but I do care how close I am to that true answer. This is because those ODEs are relying on the new information each time step. So even a small percent error can end up having very large results. So note when I look at that error, in this case, unless my error criteria is really big, this is going to be rejected. So if the error, in this case, I would then half the steps again. So instead of going to this size, I would take, say, a step of this size. In this case, I would get a smaller down step, but I would still get a relatively large error. Then I can do the step again and again, and eventually when I get small enough, I'll get a movement along this line itself, and I can keep going. So in essence, if the error is below some sort of value, we accept that value, and if not, we are going to do that halving again. Let's go in and do a quick example, and this will serve as the example of these adaptive step sizes. So we're going to solve dy dt equals y from t equals 0 to 1 with an initial step size of 1, and we're going to include an error of 0.5. Let's say for the sake of this argument that y at t equals 0 is equal to 1. So first we're going to take our normal step size, and we're going to use just the normal Eulers. So we'll say yi plus 1 equals yi plus dy dt times h. So let's say h equals 1. So y at t equals 1 is equal to y at t equals 0, which is 1, plus dy dt, which is y. So that's just 1 times 1. This is going to be equal to 2. Okay, so now we cut our step size in 2. So maybe let me pick a different color. So let's put h equals 2 here. In this case, I'm going to take 2 steps. So first I need y at t equals 1/2. Oops, sorry, instead of h equals 2, sorry, we should cut it in half. H equals 0.5. There we go. So y at 0.5 is equal to y1 plus my derivative, which is 1, times my step size of 0.5. This equals 1.5. So now I need to go to my next step, my second step at t equals 1 is my previous step, so 1.5, plus my derivative, which is 1.5, times my step size of 0.5. This, we can do out the math, and this will equal 2.25. Okay, so if I compare these two numbers, you can see that the error is 0.25, which is much bigger than the 0.05 of that qualification. So I can go ahead and cut this in half. So you can say h equals 0.25. And I'm not going to go and do this out, but it takes quite a few steps. And when I use h equals 0.25, y of 1 ends up being 2.44. Well, we're getting closer, we're converging, but we're still not there yet. We have to cut it in half again. And I'm not going to do all this out, but finally, when I get to h equals 0.0625, I find that y1 is equal to 2.637. And if I go one step further to h equals 0.03125, I find y1 is equal to 2.67, and we're finally below that cutoff criteria. Right, so in the end, I needed to cut this in half quite a few times in order to get below that error. But I'm going to sort of refine my answers as we go. This idea of cutting my step size in half again and again is good because I'm going to improve my error every time. However, even this relatively simple problem, we saw that we needed to cut that error in half many times. And I'm not necessarily getting, I'm not able to reuse information from one step to the next step, which makes this rather expensive. One way around this is the idea of an embedded Runge-Kutta system, or in another word, a Runge-Kutta-Feldberg method. The idea is going to be that we're going to take two different orders of Runge-Kutta. Remember, last time we talked about that fourth order Runge-Kutta. Here's that equation, and then I'm also putting in our third order Runge-Kutta, one less order of the Runge-Kutta equation. Remember, they're differing by what these different k's are, and then what those coefficients are. In both cases, though, each of these k's have a similar equation. What's going to be interesting, though, or what we're going to do, is we can solve out the iteration, the next step, using this sort of third order Runge-Kutta method, and we can find out what yi plus 1 equals. That y plus I1, right, is what's used to calculate K4. So essentially, we're getting K4 for free, right? I'm looking at that step. What we can then do is calculate what y1 is from this fourth order Runge-Kutta. All I need to do is use, of course, that number that I was going to calculate more or less anyways. When I do this, I can subtract the two answers off from one another. This is going to give me information about what my error is. Specifically, if I plug these two equations into each other, I end up with this equation, right? So if I take this top equation minus that bottom equation, I end up with this equation here. This is going to tell me what my error is. So I'm going to get information about my error, and then directly I can determine if I want to accept it or not. If I don't accept that move, then I can go ahead, cut my time step in half, or some other smaller step size, and redo the system. The benefit is, if my error is low, I've calculated K4, and K4 is the next K1 step, right? So if I'm looking here, I jump forward, I calculate my derivative at this point, which then goes back to reprime that point, and then I can sort of go forward. If my error is very low, those are identical, and I get to keep that information. I'm not going to do an example of this because it's long and tedious, but the ideas are the same. I'm going to go through, calculate the yi plus 1 two ways, check and see if I get the same answer, or in other words, if my error is low. If it's low, I get to continue on. If not, I need to change my step size. This is the idea behind some ODE methods. So MATLAB has several built-in functions that are going to do this for us, that have already implemented this idea of variable step size. So they're called things like ODE 2.3, ODE 4.5, and ODE 1.1.3. There's slight differences between these because one is that second and third order Runge-Kutta versus fourth and fifth order Runge-Kutta. Both are using adjustable step sizes. In general, this ODE 4.5 is the way that we want to at least start out our approach. This is that nice balance of speed and accuracy. We'll come back in a little bit. And see cases where ODE 45 is not going to work. Also, if we have a very expensive function or complex function, we might want to go to this more advanced method, ODE 1.1.3. But I recommend starting out with ODE 45. Let's talk about how we can implement this. This is going to look a lot like the functions that we've written and talked about so far. We make a function called, say, ODE 45, and then we're going to pass into that the function, so an anonymous function that's going to return a column vector for the right-hand side of the equation, right? So it's essentially that dy dt. We then are going to give it the range of t's over which we want to solve the equation. And then finally, the initial vector. ODE 45 is going to be able to handle just one equation, so just one ordinary differential equation or simultaneous ODEs. So that means that y0, if it's only one function, is just one vector. If it's one number, and if it's if there's multiple vectors, if there's multiple functions that you're solving simultaneously, we need to have multiple starting vectors. Okay, so lastly, sort of one last thing within t-span. So if we give only two values, say 0 and 45, the MATLAB will solve from 0 to t equals 45. But if I have more than two entries, let's say I have like a big long vector, it's going to solve over 0 to say 45, but it will only report at given vectors of interest. I now want to show you an example of using the inbuilt MATLAB problems. We're going to look at a predator-prey problem again. Remember from last time that this is a case where we have one set of variables or two sets of variables, so y1 and y2, which are changing, and they're both dependent on each other. In this case, we're going to use these formulations of the predator-prey model with dy1 dt equal to 1.2 y1 minus 0.6 y1 y2, and then dy2 dt equals 0.8 y2 plus 0.3 y1 y2. Let's go in and use those in MATLAB, and I'll see you over there. So here we are in MATLAB. The first thing is to implement our function that's going to calculate my derivative. In this case, I'm going to call it pred-prey, just like we did the last time. Here, I'm going to take in t and y, and I'm going to return the derivatives of my two equations. So I have to stack them because I have two equations. So I'm going to put one on one row. So this is the first equation. So this is for y1. So 1.2 times y1 minus 0.6 times y1 times y2. And then in my next row, I have negative 0.8 times y2 plus 0.3 times y1 times y2. So this is going to be my equation, my function that gives my derivatives. Then in a script, I can put in all the pertinent information, right? I can tell it I want it to run from time is 0 to time is 20. I can input my starting criteria. Here I have, I'm going to assume that at t equals 0, y1 is 2, and at t equals 0, y2 is 1. I then make my call to ODE 45. So I'm going to get out both time and y. So I need to put in those brackets. I have ODE 45. Then I put in my at pred pre. Remember that at is going to tell MATLAB that that's a function that's going in. Then I put in my t-span, so that vector, and then the vectors of my y. And then I'm going to plot a few functions. So let's see how this is going to go. So all I need to do is go up here, click run, because it's a function. And now we see my two functions arrive. So let's look at my two figures. So as you can see here, let me pull these apart. We have my y1 and my y2 varying with time. So we have that nice repeating pattern. And what you'll notice instantly is I didn't have to go through here and check, how many steps to take, right? That ODE 45 is going to do it for me. It's going to go in and do adaptive steps in order to make sure that we have that nice constant value. We can see that in the phase plot. So remember, before with Euler's method, when we did this, we had to go in and do a lot of iterations, right? We had to make that step size very small, and we had to pick it. In this case, we have this nice function value. We don't see any deviations off of this circle, and we didn't have to pick any step size. MATLAB's going to do it for us. So this is showing us how much easier it is to use the inbuilt MATLAB functions. Let's go back to PowerPoint, talk a little bit about some other options that we can put in to MATLAB that'll give us a little bit more control without us having to write the functions ourselves. So we have a few other options that we can put into that. So we can control things like how tolerant we want to be. If you remember back, we said that we could accept a move with these Runge-Kutta type approaches by using different tolerance factors. So we could put in what we want to be as the relative tolerance, the absolute tolerance, and then we can also control functions like initial step size. How big should I take that initial step size if we want? And we can also put in things that sets a maximum step size. So say, no matter what MATLAB wants to say, don't go beyond a certain value. We do this with options that are controlled by this function called ODE set. So what we do is we go into the system and we create this new variable called options. Within that options, we call a function called ODE set, which is going to take in these various pieces of information and some variables that are going to go along with it, and then pop them into my ODE solver. So we can put in things like relative tolerance, which will just relative tolerance, absolute tolerance, or abs_tol, which will control the absolute tolerance, initial step size, and max step size. Let's go in and see how this is going to affect the functioning of the ODE solver using a new function. So here we're going to use, we're going to solve this equation, dy dt equals 10e to the negative t minus 2 squared over 2 times 0.075 squared minus 0.6y. This function is chosen because it's got quite a large change in the steepness of the function as it goes. This is going to help us understand how changing the effects of the tolerance will change how this function looks. So I'm going to see you back in MATLAB in just a second. Okay, now we're back in MATLAB. So we're going to input our different functions. So here's the just main function describing the ODE. We're going to call it dy dt. It's going to come in and calculate that expression that we had on the previous in PowerPoint. Then I'm going to go in as a script and call ODE23. I'm once again using the @ sign to refer to that function, and then my t-span and my initial value. I'm then going to do this again, but this time using the options set, where I'm setting the option relative rel-tol, so relative tolerance to 1e-4. This is 1 order of magnitude lower than the default, which is 1e-3. Then we're going to plot them again and see what we get. So let me run this. So if I plot, if you see here on the plot, we can see that the higher tolerance, or the lower tolerance, has many more points shown. This makes sense. I have stricter tolerances. I should see more points being plotted. And we see that they're bunched up around where we have these large changes in behavior. So we see here not quite a few points, but not a ton. And over here we have many, many points. So we can change that tolerance through that control variable. Now that we've covered adaptive systems, I want to look at a different way to approach complex ODEs. The first one being multi-step methods. I'm only going to cover Hume's method, but there are others out there. So let's sort of jump in here. A multi-step method is the idea that we already know a lot about the system. So far, if we're sitting so far in our approach, we've said we're going to sit at ti, and I'm going to just use the information at this point. But if you remember back to when we were talking about derivatives and integrals, we said that we would have a much better understanding if we could look at previous points, or points around the point that I'm looking for. This is going to be the idea here. In essence, what we're going to do is look backwards and use information from this point in order to move ahead. This is the idea behind Hume's predictor corrector model. And this is called the non-self-starting predictor corrector model, because we're not going to be able to start it. And you'll see why in just a second. So remember when we were looking at derivatives, we said that the central difference formula, dy dt, was more accurate if I looked at yi plus 1 minus yi minus 1 over 2h, right? So if I take that central difference formula. This is the idea in the non-self-starting Hume's method. Instead of using the forward derivative idea, I can use a central difference idea. By rearranging this case, I can get a new predictor, right? So if I rearrange this, I can get yi plus 1. In this case, it's equal to yi minus 1 plus my derivative at the point that I'm at times 2h. This should be more accurate because we have a lower error in estimating what this derivative is. The same idea is going to now come with the corrector. So in this case, I'm still going to use the point where I'm currently at. So here I'm not using that back information, but I am going to take. I am going to move forward. So I'm going to take the average slope at the point that I'm at, and then at this predicted value. The idea is with this, with the first predictor, I have a much better estimate of what the point here will be. However, I'm still using the most current possible information, aka this point right here, as I'm moving forward. Right, so here this now looks just like we had for the original Hume's method, but we're using a better predictor model. So as we're going forward, the idea is we're now using information from previous steps to make the prediction and not just my current step. Right, so we have our predictor. Using that sort of central difference formula, I'm going to go back here, project out to this new point. I know my derivative at this point, at the local point, and then I'm going to take the average of those two points. And so here we have, just as before, we have these J's and M's. This is because we can do this iteratively, just like we did with the original Hume's method. Let's put this into practice using an example. So we're going to use the non-self-starting Hume method to perform, to integrate this equation. So y prime equals e to the 4e to the 0.8t minus 0.5t from 0 to 4 with a step size of 1. The initial conditions are going to be that y equals 2 at t equals 0. We're also going to need a little bit more information because we need to look backwards one step. In this case, I'm going to provide that to you. This would say that at t equals -1, y is 0.39299953. In the real world, you would likely need to take a regular Hume's method step forward to get that first step to do the iterations. But in this case, I'm going to just provide that previous step information just so that we can get going a little bit faster. So the first thing that we're going to do is we're going to need to predict the, we're going to need to use the predictor to extrapolate from t equals -1 to t equals 1. So here we're using our predictor formula. So we can say that y1 at that first prediction is equal to that previous step. So that's -0.39299953 that I had given you previously, plus my function value of where I currently am. So that's 4exp to the 0.8 times my current t, which is 0, minus 0.5 times my current y, which is 2, times 2h, so 2 times 1. When I do this all out, I get a y value of 5.607005. Okay, so now it's time, now that I've gotten my value, I can go ahead and use the corrector. So in this case, we have y1 equals my current step. So now I'm using my current step. So this is 2, that's where I'm currently at, plus I need my current slope and the predicted slope. So for my current slope, that's 4e to the 0.8 times 0 minus 0.5 times my current location, which is 2, plus 4 times e to the 0.8 times my next t step, so that's 1, minus 0.5 times my predicted value, so that's that 5.607005, all over 2 times my h, which is 1, which gives me a value of 6.5 6.549. Okay, so this represents an error of 5.73%. So this is about 3% lower than the self-starting hewn method with no additional work, right? I already had my previous y value, so I'm already there. I'm no worse off. But I can do this. I can have a more accurate solution. Okay, so I can now repeat this just like we had before, where I can go through and do this iteratively. When I do this, I say y1 of 2 is my current value 2 plus 4 exp 0.8 times my time step now, which is 1 minus the 0.5 times 6.54933 plus my slope at my current step, which is 3, all over 2 times 1. This gives me 6.313749. So we can see that after we've done that first step, after we've done the predictor the first time, we just go back to our regular hewn model of prediction and correction. This now step gives us a true error of negative 1.92 and an approximate error of, let's see, 6.313749 minus 6.549 over 6.313749 times 100% of 3.7%. Right? So you can see that this new value is coming in at a faster rate than we had before. So we can now go ahead, we get this converged if we do this again and again, and then we're ready to move on to the next step. So here, once again, we want to do our predictor. So we go in, so our y2 is my previous step. So remember, I'm looking backwards now. So this was my previous step, was 2, y was 2. And now we go in and we calculate my e at my current step, 0.8 times 1, right? My previous time, this was 2 back, 0.5 times that old y value, 6.36087 times 2, which is my time step for the central difference formula. So giving us a 13.443 as an error, as a value, and a true error of 9.43. Okay, so we can once again go in, we can do this, use this prediction to do a correction term, and we're going to eventually converge to 15.30224, which is going to be the same as the original Hughes method, but we get there faster, right? So this is going to enable us to move through those iterations faster, because once we get into that prediction, after we get past that first prediction and we're into the correction scheme, we're using those same numbers and we're not really making significant progress. Okay, so this is all I want to cover for these prediction correction models. We're ready to move on to the next topic, which is stiffness. So we've sort of danced about this idea, But to sort of solidify it, stiffness in a system is how rapidly we have components that are going to change together with slowly changing ones. So in other words, I have regions where I have high variability with that low variability. So I'm having some sort of rapid change in these values. So an example is dy dt equals negative 1000y plus 3000 minus 2000 e to the negative t. The issue is this variable or this quantity is going to die off relatively fast. And then it's going to be taken over by these variables, which are going to occur more slowly. I can plot out this the true solution shown here. And if I look, I have very, very rapid change as long as I'm less than 0.005. But after I get past that really short step, I have this much smoother slope. It's going to be difficult to solve this stiff system. I would need a very, very small step in order to handle this. And I'd have to be very careful when I'm changing from one to the other that I don't overshoot. So I could accomplish this with very small time steps, or I can move outside of Euler's, the Euler's formulation as we've shown to date, and take a different tact. What we're going to do is we're going to move away from the explicit Euler's method, which is shown here, and enter the implicit Euler's method, or the backwards Euler's method. So remember, Euler's method used the definition of a derivative using a forward difference sum. But just like we had in the backwards, we could also use a backwards derivative, right? So if we think of how we were taking derivatives, if I had my first point, I could take a forward derivative. But if I had a point, say here, I can always look backwards to get an approximate derivative. This is the idea with Euler's the implicit Euler's method or backwards Euler's method. In this case, we set yi plus 1 equal to yi minus dyi plus 1 dth. There's two differences here. You can see that the sign is going to change, and that in the backwards Euler's method, I have an I plus 1 on this in this case. So we end up getting yi plus 1s on both sides of my equation. But remember, this dy I plus 1 is just a function. So I could plug those I plus 1s in and get an equation where I'm going to have yi's on both sides. Now, what I can do is I can rearrange this equation. So I have my yi plus 1s on both sides, and then solve it iteratively. So let's see how this is going to, let's see an example. So we're going to use both an implicit and an explicit implementation of Euler's method to solve this highly nonlinear system that we talked about. So we're going to use the explicit Euler's method with a step size of 0.0005 and 0.0015 to solve for this very narrow region. And then we're going to go in and use the implicit Euler's method. Here, I've shown you what that analytical solution is. So just because it's going to take a lot of time to take such small steps, I'm going to just sort of plot this out for you. So the explicit Euler's equation would look like this. yi plus 1 equals yi plus minus 1000 yi plus 3000 minus 2000 e to the negative t times h. If I look at that first rather rough method of interpolation, we can see that we have this sort of bouncing function. I have these oscillations. We know that that's shouldn't be the case, right? I shouldn't have these points where I have this non-continuity. We can also see that that while this solution is going to bracket the true solution, it doesn't give us very good information about what's happening. We have to go to this much, much finer step size to even approach my exact solution. Let's take a look at how we're going to do this with the implicit Euler's method. So remember, this one we are going to do out. So remember that the implicit Euler's formula says yi plus 1 equals yi minus di plus 1 dth. So we're going to plug this in. So yi plus 1 equals yi, so my current step, minus this equation with yi plus 1 sort of plugged in. So in this case, we get minus 1,000 times yi plus 1 plus 300, 3,000 minus 2,000 e to the negative ti plus 1 times h. Now, we want to take this and want to isolate, we want to see if we can isolate this yi plus 1 all on one side. Luckily, in this case, it's linear in yi plus 1, right? I don't have squared terms or anything else. So I'm able to linearize this. So what I need to do is I pull yi plus 1 minus, because I need to pull, get a minus term over here, so it should be a plus term, plus 1,000 yi plus 1h is equal to yi. Oops, sorry, I messed it up. This should be minus. There we go. Yes, minus 3,000 h plus 2,000 e to the minus ti plus 1. This we don't care, this ti plus 1 we don't care because we know what that's going to be, right? That's just my current t plus 1. We don't need to solve anything for that. So that gets to stay. This over here we can manipulate. We can pull out a yi plus 1. That leaves me with 1 plus 1,000 h equals yi plus 3,000 h minus 2,000 e to the negative ti plus 1. And so we can get I plus 1 equals yi plus 3,000 h minus 2,000 e to the minus ti plus 1 all over 1 plus 1,000 h. So now we can put in any sort of h that we want and solve for this. We can see that we can use a much larger h step size, and we end up fitting that exact solution, right? So in that first step, we've only taken one step, we're already matching the exact solution. So if we compare these two, if I take a step, in this case, here, 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 and here, right? I'm perfectly matching. I've solved it exactly. Whereas with the explicit Euler's formula, we have to have a relatively small time step, right? So I will make a note that this function that we had was linear in y. This makes it relatively easy to solve. If, let's say, I wasn't linear in y, so let's say I had yi plus 1 equals yi plus, I don't know, yi plus 1 squared h. In this case, I wouldn't be able to rearrange it and get a very nice solution. In that case, what we would have to do is solve this iteratively, right? So we could use any sort of those nonlinear equation solvers to get the answer that we're interested in, right? So going all the way back to root finding methods. Same thing, if I had maybe, we'll call this y1, if I had y2, yi plus 1, so I'm trying to do this simultaneously, we can go back to our analytical, our numerical methods for solving simultaneous equations, simultaneous nonlinear equations that we could implement for finding each of these yi plus 1s. When we're using MATLAB built-in functions for stiff systems, we often don't want to use, say, ODE 45. We want to go back and use some of these simpler problems, just so that we're not taking steps that are too large out. We're not going too far ahead where we may get thrown off. So here we can use ODE 15, 23, and then we have some extra variables in here that can slightly change the control. The arguments for these stiff solvers are going to be the same as those for the previous solvers, and the functionality is just going to be a little bit different. If you're interested in finding out exactly why these are different, check out the MATLAB documentation page, and you can get into all the nitty-gritty guts of what these different functions are going to do. But this at least gives you a set of options to try if ODE 45 doesn't work off the bat. The other thing that we want to consider when writing a MATLAB code is something called an event. An event is going to be used when we don't know when we want the ODE solver to stop. Let's take an example and you'll see where we're going with this. Let's assume that we're going to look at a bungee jumper, but this time there's no cord and we want to know when they're hitting the ground. In this case, it's not so much a bungee jumper as a plummeter, right? And so we don't know how long it's going to take them to hit the ground, but we know that once they do hit the ground, we want MATLAB to stop. Because we don't know where it's going to happen ahead of time, I can't just put in something that says like t equals 0 to 40 seconds, because the plummeter may hit the ground before then. We need to have some way to tell MATLAB, this is where I'm going to start, and this is how to know when to stop. So we're going to solve this, and we're going to use events to do that. So remember, if we're looking at, say, a bungee jumper, we can say that the position in x, so dx dt, is the velocity, and my change in velocity or acceleration is gravity minus the coefficient of drag over the mass times my velocity squared. So how are we going to implement this? Well, first we need to implement just the base case. What's going to happen in those differential equations. So I could go in and build a function that's going to calculate dy dt. So what's my change in velocity and my x? Remember here, I need to incorporate both two values, right? So my x and my v. Here, I'm going to call y1 my x, and y2 is going to be v. So dy dt, if I go back and look at these different equations, right? So my dy1 dt is just y2, right? So that's this equation. And then that second row is going to be gravity minus coefficient of drag over mass times y2 times the absolute value of y. Now we're going to define an event. The idea behind the event is we're going to need to tell MATLAB how to detect the height. And it's going to be the location when the height passes through 0. So we need to find something, or we're going to find this to stop when we hit 0. So we're going to use this detect command. So the detect is going to look at y1, right? So the y's are going to come in here, and then y1, which remember is x, is going to be what we're going to detect. And that's going to be the first thing that the function returns, right? This is where it's going to come in. Stop int is just going to be 1. So it's just going to say 1 is for stopping. Now, we set in our direction of 0. So this detect y1, when it hits 0, it's going to indicate the stop point and the direction. 0 is going to be for, we can use for the direction. 0 can be direction is you set to 0 if you don't care which direction you're coming from. So if y is negative going positive or positive going negative, we don't care. We can set y1 if we want to look at say the y going this way, or negative if we want to go down. But this detect is going to be how we're going to evaluate the system, right? So this end event function is really going to determine when y is 0. So that's that stopping criteria. We could change this function to, if we wanted a non-zero stopping value, by changing that detect function to be, say, y of 1 minus 5, right? So if that would stop us at x equals 5, because then detect would be 0. Right? So it's looking for when this detect, so when this detect is equal to 0, the function is going to stop. Okay, so we can solve this system out. I'm not going to show it to you, but we can use that ODE set for optimize for options using the events tag and then at that end events function that we just talked about. Once again, we can set our initial y values to negative 220, sorry, to negative 200 and negative 20 for my initial starting values, and then we can substitute into this function. Right, so here we have my t, my y, and then I have these extra values t and y end that are going to be the final values of x, y, and t. We then call my free fall function, and then I tell it I go for as long as you want until we hit those stops by having y0, so my starting point, and then this infinity, go to infinity, go as long as you want, using those yi's, the options that are associated with that end event, and then information here that's those optional variables, which in this case are my coefficient of drag and my mass. Right? If I then I can then do some plotting things like print out my end time and my y end, and then plot. In this case, I'll find I hit the ground after 9.5 seconds. My final height is 0, and my final velocity is 46 meters per second squared. So probably not a good day for the bungee jumper. And if we want to plot this, we'll have the height that's coming down and my velocity. Notice that my graph just stops at that about 9.5. This is because the event has triggered and it's not going to take that next step. The last concept that I want to cover is including different conditions into your ODE code. We're going to look at that through, and the importance of checking your results. We're going to look at that through the case of Plint the Elder's fountain, which is an interesting device The idea was that water would come in through this tank from at a constant rate in through this elbow at the top, and it would fill up this cylinder. There was a siphon sitting near the bottom, but not exactly at the bottom. If you haven't had fluids yet, the idea with the siphon is as the water would fill up, the level in this siphon would increase. Once the water in the tank got to this level Y high, it would fill the siphon and start shooting out as a fountain. Because of the siphon action, the water would continue to flow out through that siphon as the water dropped, as long as the water stays above this Y low height, which is Y above that bottom of the tank. Once it hits that bottom, once it goes below that level of the siphon empties out and is broken. It then requires time to refill up the tank before the siphon can start again. In essence, the water turns off and on as a function of this tank. We can put equations to this. So if we neglect the water in the pipe, let's compute the level of the water in the tank as a function of time over 100 seconds. Assuming the tank is initially empty and we have the conditions that the radius of the tank is 0.05 meters, this height of the siphon is 0.1 meters. The radius of the output tube is 0.007 meters. The low height of the siphon entrance is 0.025 meters. And then we have the rate flowing in and gravity. So the siphon running via Torricelli's law says that the flow rate out is C times the square root of 2gy times pi r squared, where r, once again, is the small siphon, y is the height in the main tank, and c is a coefficient of discharge. We can look at the flow rate in the volume of the tank and look at how that changes. So the change in the volume of the tank with time is how much flow goes in minus how much flow goes out. If I put the area of the tank, the volume of the tank into this equation, we end up with dy dt is equal to q in minus c times the square root of 2gy pi r squared over pi r squared over of t, so the big radius. However, the siphon does not always run. This means we need to implement some sort of if condition that will turn the flow out on and off. So let me show you how we're going to do that. I'm going to stay in PowerPoint, but feel free to implement this yourself in MATLAB. So we're first going to come up with our equation that tells us the flow into it. So just like we looked at before, we have an equation that's going to be our essentially dy dt. We're going to call it Pliny ODE. It's going to take in time and some height of the system. I'm then going to introduce a global variable. So this global variable is accessible by every single function in your workbook. We have to be very careful with using global functions because it's not necessarily obvious what's manipulating it, because that variable can be manipulated in multiple places. So these can be very useful, but you also have to be careful with them, especially if you have multiple functions possibly acting on that variable. In this case, it's going to be critical because remember, this ODE code is going to get called multiple times throughout the solving of the ODE. And so this siphon variable is easy to be retained as we move into and out of solving for the derivatives, and is accessible to the ODE solver, which is going to need to do projections. So first, after we define that global variable, how we know it's global, because it says global right there, it's going to be called siphon. we give it all of those input parameters, so just those constants. Now we implement our if condition. So we say if my height of y, right, so y is that height getting passed in, is less than y low, turn the siphon off. So in other words, if I sort of draw out my siphon system again, if the height in the water is below y low, turn the siphon off. So siphon is going to be 0. Else if the height is above y high, turn the siphon on. So notice these variables aren't changed. So siphon is not changed when y is between y high and y low, right? So I only change it if I go above or if I go below. Now I can implement my Q out formula. So instead of sort of wrapping it all together, I'm going to have a separate y out that I'm going to then interact with. So I have that same y out formula from the siphon function, and then I multiply it by the siphon variable. So if the siphon's off, so siphon is 0, it's 0 times that function, it's not going to be siphoning. If if siphon is 1, it behaves just like it normally would. I then can define my change in y as q in minus q out over pi RT squared, and that's going to solve that function. So in essence, I have this siphon variable that's going to be determined, and it's not going to be passed into or out of this function, but it's known throughout the system. And we have these if statements that are going to change the behavior of this function depending on that global condition. I can then leave that subfunction call and write a script that's going to then conduct my ODE solver. Notice again, I'm going to call my siphon function. I'm going to just set up in the script that this function is a global function here as well. You have to have this in all these functions where you want to interact with siphon. Then we can go about our normal procedure of setting up this ODE run. We first set siphon to 0 because at the beginning, right, the tub is empty, so that should be 0, right? It shouldn't be siphoning off. We then give our t-span 0 to 100 seconds and our initial height of the tank, which is 0. Then we call our ODE 45 just like we normally would, calling on Pliny ODE, t-span, and y0. Then we can call our function. So before I enter this, let me just remind ourselves that ODE 45 is a pretty good method, right? It's got adaptive H spacing. It's using Runge-Kutta at that 4th order level. So it should perform, at least we would predict it should perform relatively well. So let's see how it does. So at the beginning, like expected, the water level in the tank fills until it gets to the height of that siphon level. And then it starts to empty. But oddly, it doesn't go all the way down to the level of the tank. So that doesn't go down to that y low, which would be somewhere down here, right? Before it starts going back up again. And then it goes down and then up and then down and then up. But we would expect it to hit this y high and this y low every time, right? There's no reason that that level should start increasing again before it goes all the way down. So what's going on? Well, the issue is that our predictors are jumping the siphon. So when I'm making my projection forward, those predictors, so those K1, K2, K3, etc., are jumping to a case where the siphon gets turned off or on prematurely. what this is saying is these projections are actually hurting us. So we're moving on to and off of that state when we shouldn't have. So what can be done? Well, there's a few possibilities. So the first possibility is to take a much smaller time step so that we don't end up jumping onto these states. When I go, right, remember I sort of make some of these projections and these errors. So we could take a much smaller time step. Or better yet, I can tell MATLAB to use a constant time step with this, with a different variable call. So remember, RK4 sys was a function that we built for a system of ODEs using the fourth order Runge-Kutta. Here, we're not going to do those possible double jumps, and we're going to have a constant step size. So we're not going to end up having cases where in maybe the short case, I'm getting always T-on, but then in the longer steps, I'm getting both T-ons and T-offs. So sometimes these simpler methods are better. So if I do it with this fourth order Runge-Kutta operator, which doesn't have adaptive systems, we can go and we can see that we bounce up and then down, all the way up, all the way down, all the way up, all the way down. What this is telling us is that sometimes the fanciest systems are not the best way to solve problems. Sometimes if I get illogical answers, we need to go back and change the system, sometimes to simpler, whether that be a fourth order Runge-Kutta or even going all the way back to Euler. Remember, if I take a small enough step, Euler is guaranteed to work. So this is not only should you take away the fact that we can use things like global variables and that sometimes we need to take a step back and use simpler methods, but you should also take away that we need to think about our solutions. We shouldn't just blindly believe whatever the computer is telling us, especially as we're going through, as you move to more complicated systems, that intuition and that understanding of what the solution should look like is going to be critical. And this is where your engineer's eye will come into space. So that's everything that I wanted to cover for today. So as a review, we talked about adaptive methods, particularly the step halving and Runge-Kutta-Fehlberg. We talked about multi-step methods such as the non-starting Hunes method. And then we talked about stiffness, particularly the explicit Euler's method and implicit Euler's method and the differences between the two, and how we can use MATLAB for solving ODEs, including events to generate stops in our solving. All right, see you in class.